Hello everyone, Satyajit Pattnaik here and welcome back to my channel. Today's topic is about vanishing gradient problem. Exploding gradient, we shall be keeping that for the next video. Today's video we shall be focusing on what is vanishing gradient problem. In the last video we learned about what is the chain rule of backpropagation, and before that we learned about the basics of neuron, backpropagation, forward pass and a lot of concepts. Today's topic is more focused on the vanishing gradient problem. So let's get started. We'll talk about vanishing gradient problem. In the last class, we paused at a very crucial point where we took derivative of a sigmoid function and we showed you that the sigmoid function lies between 0 to 1. The derivative function of a sigmoid function lies between 0 to 0.25. Right. But what's next? What is the problem that is occurring because of that? So today's video is all focused for that part. I'll be talking about the theoretical part ahead first, and then I'll talk about why and how the vanishing gradient problem occurred and what was the fix for that. So in 1980s, we were using very shallow neural networks with 2 or 3 hidden layers max, and with sigmoid activation functions, and we didn't had ReLU. ReLU was introduced in 2001. So with sigmoid function in all the layers, the gradient kept vanishing as the derivative of a sigmoid function is within the range of 0 to 0.25. Hence, with even 2 layers, the gradient will be okay. This is just theoretical. Let's go back to the problem. Let's go back to the image where we can easily understand what exactly the problem is. So just as I already told, using sigmoid function, all the values are within the range of 0 to 1. Let me just draw it again. Quick recap. It always in the range of 0 to 1. And if I draw the derivative of a sigmoid function, it is always within the range of 0 to 0.25. Okay, let me write the formulas again. Right. So in the process of backpropagation, all the weights are refreshed, all the weights are changed, right? They are updated. So the formula for, let's say, for one of the weight, which is w11 new, is nothing but w11 old minus eta of learning rate w11 old. This is nothing but my learning rate. This is nothing but my this is nothing but my loss function, and this is nothing but my learning rate. Okay, so this is my formula. And we already knew what is chain rule of backpropagation. dl of dw11 old is nothing but, not dl, dl with respect to o21 multiplied with o21 with respect to o11. My bad. So this will be derivative of o21 with respect to derivative of o11 multiplied with derivative of o11 with respect to derivative. Okay, this is nothing but my chain rule of back propagation. I'm just writing it as CRB. Now, what is the problem with this particular problem? Like, why this problem occurred? As we already know, that derivative of a sigmoid function always ranges between 0 to 0.25. Now, what is the best case scenario? The best case scenario is getting the value of 0.25, right? That is the highest value. Now, just imagine I have 3 hidden layers. I have 3 hidden layers. And in each and every hidden layer, I'm using my sigmoid function. And the best case is 0.25. Okay, so what will happen? So let's say my previous weight, which is let's say W11 old, is nothing but, let's say, define it as 5. Now, W11 new, what will be W11 new? It will be W11 old minus eta of dl by dw11 old, if I'm not wrong. Okay, now what is this? This is my previous value 5 minus eta. What is eta? Let's take my learning rate as 1. So 1 into derivative of dl by dw11 old. So this is nothing but I'll apply my chain rule here. So let's say we have three hidden layers. So there will be something multiplied with something multiplied with something, right? And that something, I'm assigning it the best possible value, which is 0.25, because we are using sigmoid in each and every hidden layer. So what will be the best case scenario? Let's say, where is my cursor? Okay, cursor is here. 0.25 multiplied with 0.25 multiplied with 0.25. So that is nothing but 5 minus 1 into, let's calculate using a calculator, 0.25 multiplied with 0.25 multiplied with 0.25. What is the value? 0.15. 0.015. Now if I do minus 5, that means the value is 4.98. You can see the value is 4.98, and that is the best case scenario which I told. Now if I talk about the worst case scenario, the worst case scenario will be almost zero, right? So in that case, if one of the terms is zero, this entire product will be zero, right? So in that case, my new weight will be my old weight, right? My new weight will be my old weight. This is actually, as I told you, in 1980s and in 1990s, we were just using neural networks with just two or three hidden layers. That was the reason sigmoid was still working fine. But in today's world, we cannot achieve anything in just two to three hidden layers. And let's say we are using 10 hidden layers or 20 hidden layers, and in each and every hidden layer, we are using sigmoid activation function. So if I do this, so old weight minus learning rate multiplied with 0.25 into 0.25 into 0.1 into 0.2 into something something. So this will be almost negligible to zero, almost zero. Because in decimals, if you keep multiplying the decimal values, it will be 10 to the power of minus something, minus 10, minus 20, right? So ultimately, your new weight and your old weight are almost similar in these cases. That is basically called as the vanishing gradient problem. That's why sigmoid shouldn't be used in each and every hidden layer of a neural networks. And that is the reason why ReLU was introduced in 2001. And we usually recommend people to use sigmoid function in the output layer if you are working with a binary classification problem. You can use sigmoid functions in one of the hidden layers or two of the hidden layers, but using it in all the hidden layers is not recommended, because you will definitely get this situation where you will have vanishing gradient problem. Okay, so that was the reason ReLU was introduced, and we'll also learn about ReLU, right? If you haven't known about ReLU yet, I also have a video regarding ReLU activation function. You can go back and understand, but practically I can show you how vanishing gradient and exploding gradient happens in a real neural network in one of my future videos. That's it for today's video. That was all about the vanishing gradient problem. In the next video, we shall be learning about exploding gradient problem. Thank you. If you like the video, please like, share, and subscribe. Don't forget to hit the bell icon in case you want to get notified on my future videos. Thank you, everyone.